work also. So errors and let us first of all do some motivation about the task itself. Some tasks in human life, and we need to check human how to be said how well he or she is doing right now. For example, for drivers, for drivers, maybe drivers, and so on. As there are a lot of actually jobs where you need to check the health of the person, and it's easy to do with some with eye scanning, eye photographing, and the idea here of our task is be working with infrared image of an eye for a person, and we'll be trying to divide the image of a pupil and of an iris from the other parts of the image. This with NPP video mix company, they have provided us with the data set, and we have make the markup for it. So the idea here is that there is an image of an eye, and we need to separate the iris image and the image of an pupil. We use binary masks, which has been which we are trying to predict, and the data set itself consists about 10,000 images, and the first part of it has been is containing 100 images, and this is about iris segmentation, and this from 8 subjects. The second is related to it contains 7,300 hundreds of snapshots of pupil, and it taken from 21 subjects. Okay, so our the already network, which has been modified with using the attention blocks. We are doing processing for of an image, and the preprocessing is pretty standard. It's just resizing, normalization, and Gauss filtering. And as an input, we use generalized unit with attention block. Introduce the attention block itself. The attention block has been invented in different paper. I mean, not by us, with connection to that. So we have as an input the evolution feature maps made several convolutions, one by one convolutions and transpositions, and after that we use the attention map to apply it to the to the same image with one by one convolution, and these are so-called feature maps, which have been used by them. So we have as input we have feature map some convolutions, and the output we have the same feature map which has been reweighted with attention. So most actually important part in the whole line, at least according to my opinion, is that how we use specific laws, but with specific addition to the laws, and I will try to explain it right now. So as you can see on the image, we have to the left, we have the this image in two halves, the upper and the lower one, and for each of the parts of halves, I could be saying, for each of the parts we are doing what? We split again this part by several. We take 4 parts for each halves, and we finding the specific points where there is there is a limit of a pupil or an iris. So on the image you see the limit of an iris to the right and to the left of the second part of the upper half. So there are 2 points where which we have been detecting. We have detected this, and we I cannot say fit, but formally it is fitting. We fit the straight line with these 2 dots, and we make the same procedure for the all the parts, for upper and lower parts also. After we have done this specific procedure, we have that figure which consists of parts of straight lines, and this figure is actually really bad bad segmentation of an image. And what we actually want, we want that our network will segment better than this bad rough segmentation. And to be sure that this network will be working like that, we actually making this thing. So we finding several dots, several, I would say, regions where, if we're talking about upper part, if we're talking about upper part, where these parts are above this line. So if we look at the image, you can see that in the bad condition there is nothing above the line. In the good example, for example, if we took a look at the lower and the rightest one, there are some additional additional area which should be selected as the iris area. So what we're trying to do, we're actually measuring how good, how much of area are above or below for the lower part the lines we have been produced. And we have a threshold which is the hyperparameter of our method. And if our model is showing the segmentation where the additional area additional to the this simplistic linear segmentation area is lower than some threshold, then we say this is a bad segmentation and penalize our model additionally. And if it is higher, it's larger, then we say it is a good model and we are not penalizing it. So main idea, again, this is an additional regularization or on our model to ensure that it will be looking for the more area of an eye. The idea here, underlying idea for this additional loss is that we know about an eye and typically image of an eye that it should be somewhat convex. It should be some convex figure, and we know this is every condition, but due to some artifacts in the images and in our processing, the segmentation could be not convex, and we're trying to how to say to add some motivation for our network to make convex convex segmentation. So this is the experimental results for our model in comparison to other models that have been tried for this data set. These models are models used for this task in different studies. And this is, for example, Deep Iris or INET. They are specifically used for iris and pupil segmentation. And we also have tried several additional variants of UNet in combination with ResNet and EfficientNet, and we compare it to our model, which is UNet with self-attention and specific loss function, and we show that our result is significantly higher than the present. So the conclusion here is that we have we are releasing the data set of pupil and iris segmentation, the markup, and we have proposed a custom architecture for this specific task, which has been shown the best results for our data set. And we show that the usage of our specific knowledge of a task is really really important, and it allows us to achieve results for the iris pupil segmentation. So that's it. Thank you for your attention. I would like to answer some questions.
Thank you, Valentin. Colleagues, any questions? Oh, please come here. The microphone is oriented.
Thank you for the presentation. Can you open the slide with experimental results?
Which one?
Yes, this one. So you compared some existing models with yours, but what about speed, performance?
Yes, thank you for your question. Actually, regarding the UNet, they are all roughly the same. And as far as I understand, the previous solutions like INET are, since they are smaller, they are faster than ours. But it's not like the 100 times faster, maybe a few times.
But your solution is efficient.
Yeah, efficient. Yes, we're showing that we have better quality.
And what your hardware is?
These results are all achieved on the same hardware, and the hardware is, as far as I remember, I'm not really sure, but I think it's V100, NVIDIA V100 GPU.
GPU. Yeah, thank you.
Yeah, of course. Thank you for your question.
Any more questions? Then for me, I have, in fact, I have no questions. I understand all that you are saying. Well, I am specialist just in this field. I saw many works of such kind. My students and postgraduate students do something like this. Just I want to add some comments and one question maybe. Do you pay attention or extract specifically geometric position? Geometric positions of pupil and iris. So both of them can be modeled as circles or ellipses. So each circle has 3 coordinates, center and radii, 3 parameters. Ellipse have 5 parameters. Do you pay attention to extracting these parameters solidly? Not the region as you painted here, but these 3 numbers.
No, we have been like extracting the parameters themselves, but we are approximately like them in some way.
I understand that we can find these parameters from the mapping, from these yellow maps. Well, yeah. But I should say that in all applications of iris, to the best of my knowledge, in medical application and in iris recognition, it's the most valuable thing is these 3 parameters of the circle of pupil and 3 parameters of the circle of iris. These yellow maps play second role. Each real task in medical images, you should measure pupil with very high precision, pupil diameter or pupil radius, radii. And iris radius. So these maps are not very good as a final result. In fact, you should extract 3 parameters, totally 6 parameters. And in most applications, this will be enough. So I advise you to pay attention to this aspect.
Okay, thank you.
I understand pretty well that this approach with neural networks is very straightforward. Neural networks are very good in painting such maps, yellow maps as you show us. But this straightforward is diverts us from a real task, in fact. Also I should say this about intersection over union, which you use as a measure of accuracy. In fact, also diverts us. You should measure the accuracy as, in real applications, you measure the accuracy as displacement of pupil center you have calculated from real pupil center and displacement of radius from real radius, and also inner part of iris, which is around pupil, is much more valuable than outer part. So you should also account for this. And this scale you measure in the slide, likely you have it, k sub I x plus b sub I. So
Yeah.
you use parameters k and b as parameters of the line. I should say that this is maybe not very good choice because for vertical or close to vertical lines, these parameters are very big and the scale of k and b is not uniform. Maybe I can advise you to go to polar coordinates and use rho and d in polar coordinates, rho and phi. So
Okay.
angle of inclination. This scale is uniform and it's used in half transform, for example, for lines, just because it's good for this task. So well, okay.
Yeah. Thank you for your really helpful comment. I think we'll continue on to work on these tasks, and we'll of course take into account your professional opinion. Thank you.
Well then, thank you. I think next presentation. Who is the presenter?